You expect me to have like a freaking flannel set?
I will get started. I think it's time, give or take a minute. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to give us insight, help us to clarify what we do, and that we'd just remove any questions that remain about the musical morphisms and all this Hodge duality and stuff, Lord. In the name of my prayer, Jesus. Amen. All right, so first order of business, I should define for you what on earth I mean by a metric. So we'll talk a little bit about metric geometry, not really that much. So basically, a vector space V over R paired with a metric G is called a geometry. And so, of course, that begs the question: what's a metric? All right. So here's the definition. G, a mapping from V cross V to R, is a metric if it has satisfying few conditions here. Number one, G is bilinear. We already know what that means. Yay. Number two, G is symmetric. We already know what that means. Yay. All right, so it's a symmetric bilinear form, and it also is non-degenerate. And the way we judge that is that if G of xy is equal to 0 for all x in V, that implies what? Y is equal to 0, right. So that would give us so-called a non-degenerate form. So this is different than an inner product, all right? A inner product is also a bilinear symmetric map, but we don't say non-degenerate. Instead, for an inner product, what is 3 replaced with? What's that?
Positive definite.
Positive definite is correct, yeah. So positive definite is that the inner product of x with x is equal to 0 if and only if x is equal to 0, right? We are not supposing that here about a metric. It turns out that positive definite implies non-degenerate. So like every inner product is a metric, but not every inner product is, not every metric is an inner product, rather. So like example 1, if we let Rn be my vector space, and I let G of xy simply be the dot product of x and y, this defines a metric. This is known as the Euclidean metric, right? What are the components? Gij, right? If we do EI dot EJ, and here I am using the standard basis. Last time I was using EI and EJ, I guess also as a standard basis for the most. I mean, I admit a certain hypocrisy. I sometimes use E sub I as an abstract basis, but not always. So if in doubt, ask me. But this, of course, the dot product of EI and EJ is, well, it's Kronecker delta IJ, right? So, which, we could also see this as like X transpose times the identity matrix times Y. So if you wanted to, you could define the matrix of the Euclidean metric. The matrix of the Euclidean metrics is just the identity matrix, all right? So Rn paired with the Euclidean metric defines a geometry which we commonly call Euclidean geometry, all right? And of course we could do more. We could define angles, notions of parallelism, all that stuff, all right? But that's not really where we're interested in here at the moment. Example 2, R4 with g of xy equals to x transpose eta y, where here eta is minus 1, 1, 1, 1, otherwise 0, right? Specifically here, g of xy is minus x upper 0, y upper 0, plus x upper 1, y upper 1, plus x upper 2, y upper 2, plus x upper 3, y upper 3. This is the so-called Minkowski metric. This is the metric which describes the geometry of special relativity on space-time, right? This is you can think of x upper 0 as time, and x1, x2, and x3 as space, like 3 spatial dimensions. And this is not an inner product because there are things called null vectors. Check this out, right? If I take g of the vector, 1, 1, 0, 0 with itself, what happens? We get, minus 1 times 1 plus 1 times 1, also known as Shane has pointed out, 0. So this is an example of what's called a null vector. A metric can have quote-unquote null vectors. Null vector is a vector whose, the metric of that vector with itself is 0, despite the fact that the vector is not 0. So working with a metric is more subtle than working with an inner product. There are beautiful theorems which are true for inner products. Some of those theorems are still true for a metric, but it's dicey, all right? The study of properties of metrics is much more nuanced than an inner product. Inner product is nice. Metric, all right. Yeah. Okay, so anyway, in this case, Gij is, you could say it's, well, the case-wise defined, right? It's minus Kronecker delta 0i, Kronecker delta 0j, oh, goodness gracious, this is horrible, plus, I don't want to write it out. Forget this. Minus 1 if I equals to j equals to, oh, apparently I'm using 0 as an index, or 1 if I is equal to j is greater than or equal to 1, 0 else. What I'm trying to say in a nutshell is it's like that. All right. Okay, so that's what I mean by a metric. Those are pretty much the only 2 examples I have in mind for now. All right. And what? Which what?
The top right corner is 0, 0, not 1.
Well, I have numbered things 0 to. I've used R4 with coordinates 0 to 3. You could do 1 to 4. You just have to adjust my formulas. it's really up to you. But I think I use 0 to 3 typically in the notes because I'm trying to make contact with physics books, which use 0 to 3. So did I just hear a gross? You guys are such math majors. It's almost like you're math majors. All right, so yeah. All right, so
Did I hear you applying that?
let us talk about metric duality for tensors, aka musical morphisms. I know, right? So
Is it choreographed?
let's see here. Oh, is it choreographed? All right. I got to make sure I don't skip the wrong. I got to make sure I don't skip the wrong definition, guys, because if I do, we'll be up a creek, you know. It's here. I don't think we need definition 7.44 at the moment. I'm going to ignore that and hope that it doesn't catch up with us. So I do need to definition given V with basis, you know, V1, V2, dot, 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 Vn, all right, and metric, I guess I could say E1. I don't know, I'll make up my mind eventually, guys, here. Basis like that, and metric G, which of course we could write as the sum over I and j of Gij, E upper I, tensor E upper j, using the usual dual basis like we've talked about before, has, you know, Gij. How's that equal to? That's equal to G of E lower I, E lower j, per our discussion last class, right? I'm not saying anything really new here. You know that this is symmetric as well, okay, because it's a metric, so it's symmetric. There exists then G upper ij exist such that the sum, let's say, k equals 1 to n of G lower I k, G upper k j is equal to the Kronecker delta ij. If you forgive me for not sticking with the index conventions here. Some people would write lower I, upper j there. I hate that. I don't know why. I just don't like it. So what I'm trying to say is that this G upper ij, if we think of them collectively as a matrix, it's the inverse matrix. It's the inverse matrix to the matrix of the metric, right? So like if I was to define big G equal to the n by n matrix with components Gij, has G inverse as the n by n matrix with components G upper ij. So this is referred to as the inverse metric, but please understand, I'm not saying inverse as a function. I'm just talking about inverse as a matrix. I mean, the metric goes from the Cartesian product of the vector space to the reals, right? And inverse to that is not possible. You know, yeah. Okay, so that's the inverse metric. Notice the use of the up-down indices. So that's the inverse metric. Once we have that, if we're given a vector, let's say V upper I, we can define v lower I to be equal to the sum over j of gij v upper j. And likewise, if given a covector alpha sub I, we can define alpha upper I to be the sum over j of g upper I j alpha lower j. And when I say we, I'm really talking about physicists. All right? This right here is called raising, this is called lowering the index. And here we're raising the index. All right? We can lower the index or we can raise the index using either contraction. We either are contracting across the metric to lower the index, or we're contracting across the inverse metric to raise the index. Now, there's a more, and then of course you can do other stuff like, well, what happens if you raise it and then lower it? Do you get back where you started? I sure hope we do. Otherwise, this notation is, cuckoo for Cocoa Puffs, right? I mean, it's not good. It's, like, what's crazy? I don't know. What's a good crazy thing? How do I illustrate craziness in our current world? So many choices.
But comparatively, there's nothing.
I don't know. There's just so many good bad things to give here. I'm just going to go with no example. And whatever I pick, it won't do justice. Left to the reader. Yes, left to the. I'll leave it to the audience. So,
Left to the ambitious.
So let's try this. So v, we'll start with v upper I, right? And I'm trying to think of how I can do this. All right, so v upper I, v lower I is equal to the sum, I'll start with this one, sum over j of g I j v upper j, right? But then if you believe in this kind of stuff, we ought to be able to lower this index, right? So we'll replace that with a sum over k. Sum over k. Let's see here. So I do a g, j, k, v lower k. See that? All right. So I lowered that index to a k. This j goes here. All right. Just like this I goes there. Okay. Then what? Well, if you look at this, this is the sum over sum over k of the sum over j, flip the finite sum, ask my Math 200 people, they'll tell you it's true. They've proved it. But what's the thing in the middle? Here's the thing, is I wrote down, oh yeah, so that's exactly this over here, right? The reason that we know what happens there. See, because the metric, and the inverse metric, they are inverse as matrices. So when you contract them across their row and column index like such, you're just left with a Kronecker delta because that's matrix multiplication. This is just the Kronecker delta. Which ones? The J's, they be canceling. We're just left with an I and a K here, okay? As you know, the Kronecker delta is the natural enemy of the finite sum. And so the K gets squashed, and we're left with a VI. As you can see, VI is equal to VI, 1 equals to 1, math. No, forgive me for putting that in this lecture. I reject 1 equals 1 proofs. Don't tell my Math 200 people. I rail against 1 equals 1 proofs. Like, no. 1 equals 1, no. I don't know.
1 does not equal
1 does equal 1, but when proofs end with 1 equals 1, therefore true, it's almost always a wrong proof. Almost without exception. But anyway, this is not a proof. This is just a demonstration of consistency of notation. That's all this is, all right? Don't make more of it. I'm just showing you, you can take this notation out for a spin and it makes sense. All right, great. Let me give you a more careful definition of, because these are the musical morphisms I just did. All right, these are the musical morphisms. Here's a better rule. Definition, given V and V, we create alpha sub V in V dual by the rule alpha sub V of X is equal to G of XV. And likewise, given alpha in V dual, we create V sub alpha of, of V double dual, right, by rule, all right, here we go. V sub alpha acting on beta equals to G inverse of alpha beta, where G inverse of alpha beta is by definition the sum over I and j of alpha sub I, beta sub j, G upper ij. And let me finish this litany of silly notation. So I think I'm usually okay. I'm replacing a vector with a form. So you might say this: flat of V is equal to alpha V. And how do you make a sharp? I'm not good at that.
Hashtag slanted.
Hashtag slanted? I slanted it the wrong way?
Don't you have to slant all of it?
No, you slanted the wrong line.
You got it.
All right.
Hashtag out. Where's my mask?
So this is the sharp, this is lowering an index, raising an index. But what that's really doing is this is real notation.
No way.
Yeah, real.
That's so cool.
Way indeed.
No.
Yes, way. Totally. So,
You actually didn't make that up.
no, I did not make it up.
That's so cool.
What, you thought I just made this up?
Because it's called music.
I'm not that clever. Come on.
It's in John Lee's textbook. It's got to be real.
I mean, it's all real. There's no complex number anywhere here, but so these are in fact isomorphisms. This is an isomorphism from V to V dual, and the sharp is an isomorphism from V dual. Here technically I said V to V double dual, but of course we can identify that with V through the canonical isomorphism of V and its double dual. So if you make that identification of the vector space and its double dual, these are actually inverse maps. Like the inverse map of the flat is the sharp, the inverse map of the sharp is the flat. That's yes, it's everything you want it to be. Okay. And you can find the index lowering stuff from here just the same, If I calculate, for example, alpha sub V acting on, let's see here, E upper I, right? That is G of E upper I acting on V, but let me put V's basis expansion in. Remember, V we can write as a sum over J of, oh man.
Should that be
Oh, yeah, it should be E lower I. What's wrong with me? I was like about to, really confused. Thank you. Thank you very much. So V upper J, E lower J, right? Then by linearity, I pull out the sum over J, and I've got, let's pull out the sum over V. So I've got V upper J, G of EI, EJ, which of course gives me the sum over J of GIJ, V upper J, right? But this is exactly what we defined a second ago as V lower I. So you see this, I mean, so alpha sub V you would write as the sum I equals 1 to n of like alpha sub V, the ith component of that times E upper I, right? Where this would be alpha sub V of EI by our discussion like last class. So what I'm trying to tell you is that the raising and lowering index rules, they can be seen as naturally attached to these isomorphisms, the flat and the sharp isomorphism. Okay, so here's the thing, is once we have a way of converting vectors to covectors, or vice versa, if we have a tensor of a particular type, we can convert it to another tensor, right, of a somewhat related type. Let me show you how this goes. So like, and again, this is one of those places in the notes where you'll have to, you know, I beg your forgiveness that my R comma S notation is now backwards thanks to Preston. I mean, it's my fault too. But I have not edited those, nor am I going to, because it's probably more important for me to work on Preston's research project and or Violet and Shane's research project, truth be told, than for me to fix the RS notation in the notes at the moment. Since obviously I'm not going to take points off, as there is now a confusion about that matter. Anyway, so getting to the point here, if we have example, what am I on? Example 1, I guess. If I had a tensor T, what's that? What? Oh, 3 it is then. So if I had T, so you guys, you tell me, what do you want the inputs to T to be? I'll take 3 inputs, any 3.
V star, V star, V star.
V star, V star, V star. V dual, cross V dual, cross V dual, all right. And of course that goes to the reals. We're talking about real value tensors. I want to create a corresponding map, let's say T tilde, which is a mapping from, say, V dual cross V, all right? So I would like to define T tilde on triples of covector, vector, vector. And I want it to be based on T. How would I do it? I'll do the easy part. T of alpha, haha. Take that.
flat X,
Flat X, flat Y. Very good. So I can convert tensor type using these isomorphisms. And if you calculate T tilde of, let's say, E upper I, E lower J, E lower K, right? that would be equal to, let's see here, the sum over, let's say, ijk, L and M, I'll use L and M for indices, why not? G, JL, G, MK, T, upper I, J, K, when you work it out. And I'd rather not work it out, 'cause it's not really that interesting, but if you sort through it, that's what happens. In other words, you know, I could have written down T as the sum over ijk of like T upper ijk, E lower I tensor E lower j tensor E lower k, right? And then T tilde is basically the sum over ijk of T upper I lower jk, E lower I tensor E upper j tensor E upper k. And the meaning of that modified, I mean this right here, right, this business right here is what I mean by that. And this is an abuse of notation to use the same letter T for both places, right? Because technically speaking, it's not the same tensor anymore, right? It's got a totally different domain. T as given takes in triples of covectors, whereas T tilde takes in a covector paired with two vectors, right? But because of the musical morphisms, we can freely transfer between these two objects, right? So physicists do this in like general relativity, especially given a tensor of a particular type, they'll use these musical morphisms to convert it to another type as is convenient for a particular equation or something, all right? So anyway, enough about that. What's more interesting perhaps for us is the extension of this story to the exterior algebra. See, because last time we saw that the p forms and the n minus p forms had the same dimension. Maybe we didn't notice that much, but we talked about the dimension of lambda p was what? What was it? Do you guys remember? let me remind you the story we were going through. N choose p, right? And we decided we didn't know the formula for that, which is unfortunate because it does have a formula. You know? What's that? Oh, you haven't taken 311 yet. Well, we can get on that. Let's see here. Working on it. Okay. Yeah, get on that. Let's see here. So, as we talked about last time, the exterior algebra to the vector space has, you know, you have 0 forms up to n forms, right? So we had like lambda 0v. And so this plus circle is just a fancy way of saying that these are independent. In all honesty, what's really going on here is just a Cartesian product of these things, and then we're adding them according to the rule for addition in the Cartesian product of vector spaces. See, any particular set of any particular set of p forms, if you add two p forms together, you get another p form, right? Because the p form is built from the wedge product of p covectors, yeah? So if I add two things with p covectors, I get another thing with p covectors, right? And you might say, well, you can't add that to something that has, you know, if I have if I have like a 2 form, I can't add that to a 3 form, right? But the, what?
It should be like p minus 1 and p.
Oh, n.
Or n.
Sorry, my bad. So, yes, so anyway, all I'm saying is like, in terms of like, if you think about this harder, what's really going on is we're just using the external direct sum of these spaces, whatever that means. You could think of it as the Cartesian product of vector spaces for those of you guys who are in 321. It's basically just that. There's no way to subtract, like these are independent. You know, there's no way to subtract a piece of the n vector of the n form from an n minus 1 form. I can't subtract anything from here from something in here really meaningfully. Like there's no interaction between these different components. They're independent subspaces. But anyway, that said, when we multiply these things, there's a well-defined multiplication, right? The wedge multiplication, in a nutshell, it takes in, if we have a p form, right, and we wedge it with a q form, what comes out? A p plus q form, right? With where lambda lambda k of v is identified to be 0 for k greater than or equal to n plus 1. Ha! Take that. Was that what you were going to say? Or no? I mean, we can't go past the top form because that would be built with a wedge of more than n things. And if we're in an n-dimensional vector space, we can't have a wedge of more than n things without a repeat. And so, yeah.
What I was going to do, that's what I was going to say, I did have to do with the repeat though.
Oh, okay. But
It was just going to be like, unless there's a repeat.
so my point is the addition of forms of different degree is not interesting. But the multiplication is, because if we take p forms and we wedge them with q forms, right, we get a p plus q form. Yeah? Example, I haven't done enough examples in here yet. Example 4, if we had something like, you know, alpha equals to e1 plus 3e2 and upsilon is equal to e1 wedge e2 plus e3 wedge e4, then alpha wedge upsilon is e1 plus 3e2 wedged with e1 wedge e2 plus e3 wedge e4. And the definition, which I never gave you, but it says that this wedge product behaves well with respect to distribution. It's associative. Scalars pull out. And as such, this gives us, you know, E1 wedge E3 wedge E4 plus 3 E2 wedge E3 wedge E4, because this piece goes to 0 because, as you think about it, what happens? In both of the distributions that you can think about, we get a wedge product of either E1 with E1 or the wedge product of E2 with E2. Either way, 0, right? And as such, we just end up getting E1 wedge that, and then 3E2 wedge that. And as you can see, we took a 1 form, wedge a 2 form, and we got a 3 form. Okay. So I do owe you some kind of silly basic examples like this, because I do test on this, believe it or not. Usually not with the E1s. I usually add dx's and dy's and dz's by the point of testing, because we will soon grow past E upper 1 and replace it with dx, and E upper 2 and replace it with dy, and E upper 3 and replace it with dz. All right? All in good time. So what I was getting at before I got distracted with this example is that there's an isomorphism. There's an isomorphism between p forms and n minus p forms. The reason that being the dimension, as you guys will prove in the homework. Phew, that was close. I almost proved this last time. Okay, let's be honest. I wasn't that close to proving it. But I thought about it, though. So this is n choose p, right, where n is the dimension. And there's a formula for that. I believe it'd be n factorial over n minus p factorial times p factorial, if I remember right. And yes, all right, yay. So
No, I'm pretty
Might be
sure.
P minus N. No, it's
No.
Is it like N minus P?
better be n minus p, otherwise I get a negative factorial. That I don't know what to do. So,
Happens all the way
Gamma
through this test.
I mean, we can check it. We can spot check it. What happens with n choose n? What you got? That's good. N choose 0. That's good. How about n choose n minus 1? Hooray. Yeah. And also, this is equal to, you know, n choose 1 as well, right? It is in fact true that n choose p is equal to n choose n minus p. Is that obvious? I don't know if that's obvious or not. It's obvious from the formula? Oh, because that,
You just trade them
you
out.
just, immediate, right. Well, that's a very dumb thing to see in the formula. It's a very profound thing as it's applied to the context of exterior algebra. It's actually quite interesting what's going on here. And so since those dimensions are the same, that means that there's an isomorphism. There's an isomorphism from p forms to n minus p forms. We just saw that the isomorphism between vectors and covectors is actually very natural in the presence of a metric. We can use the sharp and the flat maps. And something is also true about this isomorphism. This isomorphism that I'm talking about here has a name. It is called Hodge duality. Hodge duality is the isomorphism between p and n minus p forms. And it's typically, well, at least as I understand it, it has to be done in the presence of a metric. So, Hodge duality. P forms over V isomorphic to n minus P forms over V. All right. Let me give you an example of that before I burden you with what has been. Oh, I am going to burden you with what has been from last class. So here we go. Example 5. We talked about omega subvector A, right? Which was what? Was A1. E1, A2, E2, A3, E3, right? And I talked about the flux form of, say, vector B was B1, E2, wedge E3, plus B2, E3, wedge E1, plus B3, E1, wedge E2. So, what is omega, though, really? Isn't this nothing more than a sharp or a flat map? A is a vector. Omega of A is the vector, is the one form corresponding to the vector A. In fact, this is flat A with respect to the Euclidean metric. Euclidean metric's really boring because since the components of the Euclidean metric are the Kronecker delta, raising and lowering indices does nothing. Like the upper index and lower index, they're just equal. Nothing happens. For the Minkowski metric, the spatial indices stay the same, but if there's a temporal index, like the 0th index, you can get a minus as you lower or raise it. I mean, technically speaking, for a more interesting metric, raising and lowering the index could be much more interesting because your metric could have, it doesn't have to be diagonal. If it has like off diagonal entries, then it's much more nuanced, like the raising and lowering indices. Yeah.
Isn't E upper 1, E upper 2, E upper 3 the basis for vector space?
This is the flat of the vector A.
So is E upper 1?
No, these are not, V is Rn, which would be the span of E1, E2, E3 in my current thinking. V dual would be the span of the dual basis. Again, shout out to the future. But, yeah. Okay, so that's the flat mapping is actually the so-called the work form mapping, as it's called. This is not, well, you know what this is actually. So this is in fact the Hodge dual of the work form of B. So this is Hodge dual. See, Hodge duality takes in a P equals 1 form. And so here we have P equals 1. P equals 1 goes to a n minus P, which is equal to 3 minus 1 is equal to 2. We take a 1 form in, we get a 2 form out. All right? Now the Hodge dual of the flux form of B is going to be the work form of B. That's how Hodge duality works on the 2 form. Hodge duality takes in a 2 form, and then it changes it to a 3 minus 2, which is a 1 form. That's how the Hodge duality works there. And so I'm explaining right now, if you're wondering, guys, how Hodge duality works in Euclidean geometry in 3 dimensions. The exterior algebra, there's what? 1 forms, 2 forms, 3 forms, 0 forms. That's it for R3, right? So you guys tell me, what should the Hodge dual of 1 be? It has to be, right? Because the Hodge dual goes from a 0 form to a n minus 0, which is 3 minus 0 form. What's the Hodge dual of E1, wedge E2, wedge E3? Oh, no. It's so we take in a 3 form, we spit out a 3 minus 3, which is a 0 form, which means we can send it to 1. So Hodge duality is a mapping from the exterior algebra to the exterior algebra, which always acts across like degrees. It takes P to n minus P forms. And then we can extend linearly from the rules I told. I mean, these are the rules, basically. Yeah.
Is it linear?
It is linear. Yep, it is linear. Hodge duality is linear. It is an isomorphism. Like Hodge duality is an isomorphism. So Hodge duality restricted to like, P forms on V is a mapping from the P forms on V to the n minus P forms on V. All right. I say restricted because I really want the Hodge duality to generally be thought of as a mapping from the whole of the exterior algebra to the whole of the exterior algebra again, you know? In other words, I don't want to like say star sub P, because technically, I mean, you could think of the different Hodge dualities for the different levels as different Hodge dualities, but I'd rather think of them all as one colossal notion. What? No? Okay. Technically, it's not one isomorphism, right? It's actually, there's n isomorphisms here, I suppose, right? 0 to n, 1 to n minus 1. Wait a minute. Well, it goes the other way too, so. Oh, anyway, so altogether, there's a very boring equation here. The Hodge dual of a form is what? So it's alpha again, right? So the Hodge dual, if you do it twice, you get back where you started. Now this is true because we're in Euclidean space. Turns out, if we're in a more general context, that doesn't have to happen. All right, now that you notice I haven't defined Hodge duality, have I? I mean, I told you this how it works in n equals to 3, but I think I owe you, here's my definition. And the definition actually uses the index lowering and index raising stuff we did at the start of class. So these are not disconnected topics, guys. Like Hodge duality is it's part of the same story as the musical morphisms. So here it is. Definition for for V paired with metric G, all right, and alpha, an element of the P forms on V, define, I'm trying to spell, define Hodge dual of alpha to be an element of the n minus P forms on V by Hodge dual of alpha equal to, behold, the sum I1, I2, In equals 1 to n of 1 over P factorial, n minus P factorial, alpha. Now check this out. I'm raising the indices here. I've raised P indices here. And then you got your handy dandy anti-symmetric symbol, I1, I2, IP, and then lo and behold, J1, J2, Jn minus P, e to the J1, wedge e to the J2, wedge e to the Jn minus P. And I see my note, my my notes are missing something here. All right. Because I don't use, so like in physics writing, if there's an index which is up and down, it's assumed to be summed over. But I'm not working relative to that convention here, so I still owe you another summation over the J indices, right? So so there you go. That's the definition of Hodge duality. Notice here that what I mean by this business right here, what's that mean? That means alpha I1, I2, IP is by definition the summation, let's say K1, K2, Kp of G upper I1, K1, G upper I2, K2, G upper IP, Kp of alpha sub lower K1, K2, Kp, right? Where these are the usual tensor components of the P form. It's a P form, so it has P indices. They're lower because it's a P form. So there's actually not, we're raising all P indices up in order to contract them against the anti-symmetric symbol. It turns out that this is an isomorphism that's coordinate invariant. Don't make me prove that right now. So, all right. So, I wanted to give you a definition because I've not defined everything in here, and it bothers me sometimes. But I'm actually kind of more interested in seeing how this fleshes out for the example of, say, Minkowski space. Because Minkowski space actually has interesting up-down index stuff going on. And so like R4, we can talk about, all right, so we've got lambda 0, lambda 1, lambda 2, lambda 3, lambda 4, all right? Let me just, if you don't mind, tell you what's the basis elements for each one of these spaces, all right? So like an arbitrary, what's an arbitrary 0 vector? I mean 0 form, what's an arbitrary 1 form? What's an arbitrary 2 form? What's an arbitrary 3 form? What does an arbitrary 4 form look like on R4? So you just have one. This one, you've got things like E1, oh man, I got to do the 0, right? E0, E1, E2, E3. All right, you got those? Two forms, you've got E0, wedge E1, E0, wedge E2, E0, wedge E3, right? Those are new. But we also have what we had before in R3, right? We also have the E1, wedge E2, E1, wedge E3, E2, wedge E3. And I probably am going to want to not use that, but use E3, wedge E1 if I want the formulas to work out nice like they did last class, you know? How about three vectors? Well, you've got what? E0, wedge E1, wedge E2, E0, wedge E1, wedge E3, E0, wedge E2, wedge E3, and what's the last one? The last one was the end of the story for 3 dimensions, right? E1, wedge E2, wedge E3. That was the top form for R3. So what I'm writing now are the basis for 0 form, 1 form, 2 form, 3 form. 4 form is easier. What is it? There's just one. What is it?
0, wedge E1, wedge E2, wedge E3.
Cool. All right. It's probably a good idea for us to write the, let's write down the musical morphisms here while we're at it. So I'm thinking about R4 paired with the Minkowski product, all right? So I'm using G of xy equals to x transpose eta y. I like that formula personally, where eta is minus 1, 1, 1, 1. So that's the metric we're using. That's Minkowski space. What is the flat of the vector A0, A1, A2, A3? Or if you like, do you want me to use the basis notation instead? I could do that. I mean, I'm going to finish this expression. So what is this? This is equal to? Yeah, I mean, I'll just tell you what it is. It ends up being minus A0, A upper 0, E upper 0, plus A upper 1, E1, plus A upper 2, E2, plus A upper 3, E3. The minus is because of this minus here. When you work it out, that's what happens. So like the sharp